correct answer is 86. The standard mentioned is ANSI/IEEE standard C37.100-2018 IEEE Guide to the Application of Protective Relays for Power Systems. This standard defines device numbers used in protective relaying. Let's explore some of the key device numbers. Device number 21 is a distance relay. Distance relays operate based on the impedance between the relay location and the fault. They are commonly used for transmission line protection, providing discrimination based on distance to the fault. The distance relay measures the voltage and current and calculates the impedance. If the calculated impedance falls within a predetermined zone, the relay initiates a trip. Zone 1 is typically set to cover 80 to 90% of the protected line section, providing fast tripping for faults within that zone. Zone 2 extends beyond the end of the protected line section, typically reaching 50% into the next line section. Zone 3 is often used for remote backup protection. Distance relays are less sensitive to source impedance variations compared to overcurrent relays. They provide high-speed operation for faults within their protection zone. Device number 27 is an undervoltage relay. An undervoltage relay is designed to protect equipment from damage due to low voltage conditions. It operates when the voltage drops below a set threshold. These relays are used in various applications, including motor protection, generator protection, and load shedding schemes. When the voltage drops below the set point, the relay trips the circuit breaker, disconnecting the protected equipment from the power supply. Undervoltage relays are crucial for preventing damage to motors and other voltage-sensitive equipment. They can also be used to initiate automatic transfer schemes to switch to an alternate power source during voltage dips. Time delay settings are often used to prevent nuisance tripping due to momentary voltage fluctuations. Device number 51 is an overcurrent relay. Overcurrent relays are one of the most common types of protective relays. They are designed to protect equipment from excessive current flow. These relays operate when the current exceeds a predetermined value. Overcurrent relays are used in a wide range of applications, including feeder protection, transformer protection, and motor protection. There are different types of overcurrent relays, including instantaneous overcurrent relays and time-delayed overcurrent relays. Instantaneous overcurrent relays operate without intentional delay, providing fast tripping for high-magnitude faults. Time-delayed overcurrent relays have an intentional time delay, allowing downstream devices to clear faults before the upstream relay operates. The time delay is typically coordinated with other overcurrent relays to ensure selective tripping. Overcurrent relays are typically connected to current transformers, which reduce the high currents to a safe level for the relay. Device number 57 refers to a lockout relay. Device number 86 is also a lockout relay. Lockout relays are used to prevent a protective relay system from reclosing a circuit breaker after it has been tripped. They are typically used in conjunction with other protective relays, such as overcurrent and undervoltage relays. A lockout relay requires manual reset after it operates, ensuring that the cause of the trip is investigated and resolved before the circuit breaker is reclosed. These relays are crucial for preventing equipment damage and ensuring system stability. The lockout relay can be tripped by various protective relays, such as overcurrent, undervoltage, or differential relays. When the lockout relay trips, it typically blocks the closing circuit of the circuit breaker. The operator must manually reset the lockout relay after the fault has been cleared and the system is safe to re-energize. Lockout relays are commonly used in critical applications such as generator protection and transformer protection. They are also used in industrial facilities to protect critical equipment and processes. They are designed to latch in the trip position, preventing automatic reclosing of the circuit breaker. The relay typically has multiple contacts, which can be used to trip other devices or provide alarm signals. The contacts are often wired in series with the circuit breaker closing circuit to prevent reclosing. The manual reset function ensures that personnel investigate the cause of the trip before re-energizing the system. Lockout relays are often used in conjunction with other protective functions to provide comprehensive protection for electrical equipment. They are an essential part of a well-designed protection system. They improve system reliability and prevent equipment damage. They help to ensure the safety of personnel and equipment. They play a critical role in maintaining the integrity of the electrical system. You can find more information about lockout relays and other protective relays in the ANSI/IEEE C37.100-2018 standard. This standard provides detailed information on the application, testing, and maintenance of protective relays. It is an essential resource for electrical engineers and technicians working with power systems. The standard covers a wide range of protective relays, including overcurrent relays, undervoltage relays, distance relays, and differential relays. It also provides guidance on setting the relays to ensure proper coordination and selectivity. The standard is updated periodically to reflect changes in technology and industry practices. It is important to consult the latest version of the standard for the most up-to-date information. The standard is developed by a committee of experts in the field of protective relaying. The committee includes representatives from utilities, manufacturers, and consulting firms. The standard is widely used in the United States and other countries around the world. It is recognized as a leading authority on protective relaying. The ANSI/IEEE C37.100 standard also defines the device function numbers used to identify different types of protective relays and control devices. These device numbers are used in electrical schematics and wiring diagrams to indicate the function of each device. Knowing these device numbers is essential for understanding and troubleshooting electrical systems. For example, device number 21 represents a distance relay, which is used for transmission line protection. Device number 27 represents an undervoltage relay, which is used to protect equipment from low voltage conditions. Device number 51 represents an overcurrent relay, which is used to protect equipment from excessive current flow. Device number 86 represents a lockout relay, which is used to prevent automatic reclosing of a circuit breaker after a fault. Understanding the function of each device number is crucial for designing and maintaining a reliable electrical system. The ANSI/IEEE standard C37.100 provides a comprehensive framework for protective relaying in power systems. By following the guidelines in this standard, engineers can ensure that their protective systems are properly designed, installed, and maintained. This helps to improve system reliability, protect equipment, and ensure the safety of personnel. Lockout relays are particularly important in applications where it is necessary to prevent automatic reclosing of a circuit breaker after a fault. This is often the case in critical industrial processes where an unexpected reclosure could cause damage to equipment or injury to personnel. In these applications, a lockout relay is used to latch the circuit breaker in the trip position, preventing it from being reclosed until the fault has been investigated and corrected. The lockout relay is typically reset manually by an operator after the fault has been cleared. This ensures that the operator is aware of the fault and has taken steps to prevent it from recurring. Lockout relays are also used in generator protection schemes to prevent damage to the generator in the event of a fault. In these schemes, the lockout relay is tripped by various protective relays such as overcurrent relays, undervoltage relays, and differential relays. When the lockout relay trips, it trips the generator circuit breaker and prevents the generator from being reconnected to the system until the fault has been cleared. This helps to protect the generator from damage and prevent system instability. Lockout relays are an essential component of a well-designed protective system. They provide a reliable means of preventing automatic reclosing of a circuit breaker after a fault, which can help to protect equipment, prevent injury, and improve system reliability. In addition to the device numbers mentioned, there are many other device numbers defined in the ANSI/IEEE C37.100 standard. Some other commonly used device numbers include 49, which represents a thermal relay, 67, which represents a directional overcurrent relay, and 87, which represents a differential relay. A thermal relay is used to protect equipment from overheating. It operates based on the temperature of the equipment and trips a circuit breaker when the temperature exceeds a predetermined value. Thermal relays are commonly used to protect motors, transformers, and other electrical equipment. A directional overcurrent relay is used to protect equipment from overcurrents in a specific direction. It operates based on both the magnitude and direction of the current, and trips the circuit breaker when the current exceeds a predetermined value in the specified direction. Directional overcurrent relays are commonly used in parallel circuits and grounded networks. A differential relay is used to protect equipment from internal faults. It operates based on the difference in current between the input and output of the equipment and trips a circuit breaker when the difference exceeds a predetermined value. Differential relays are commonly used to protect transformers, generators, and motors. Understanding the function of these and other device numbers is essential for anyone working with electrical protection systems. The ANSI/IEEE C37.100 standard provides a comprehensive resource for learning about protective relays and their applications. By studying this standard, engineers and technicians can gain a thorough understanding of protective relaying principles and practices. This knowledge is essential for designing, installing, and maintaining reliable electrical systems. Lockout relays are available in a variety of sizes and configurations to meet the needs of different applications. They can be panel-mounted, DI and rail-mounted, or surface-mounted. They can have multiple contacts to trip other devices or provide alarm signals. They can be powered by alternating current or direct current. The selection of the appropriate lockout relay depends on the specific requirements of the application. It is important to consider the voltage and current ratings, the number of contacts, the mounting style, and the power supply requirements. The lockout relay should be selected to meet or exceed the requirements of the application. It is also important to select a lockout relay from a reputable manufacturer to ensure reliability and performance. Lockout relays are typically installed in a control panel or switchgear enclosure. They should be installed in accordance with the manufacturer's instructions and all applicable electrical codes. The wiring should be neat and organized, and all connections should be tight and secure. The lockout relay should be tested after installation to ensure that it is functioning properly. The test should include verifying the trip settings, the contact operation, and the reset function. The lockout relay should also be periodically inspected and tested to ensure that it continues to function properly over time. The inspection should include checking for signs of damage, corrosion, or loose connections. The testing should include verifying the trip settings and the contact operation. By following these installation and maintenance procedures, you can ensure that your lockout relays provide reliable protection for your electrical equipment. The ANSI/IEEE C37.100-2018 standard is a valuable resource for understanding and applying protective relays in power systems. This standard provides detailed guidance on the selection, application, testing, and maintenance of protective relays. It is essential for electrical engineers and technicians working with power systems. The standard covers a wide range of protective relays, including overcurrent relays, undervoltage relays, distance relays, differential relays, and lockout relays. It also provides information on setting the relays to ensure proper coordination and selectivity. The ANSI/IEEE C37.100-2018 standard is updated periodically to reflect changes in technology and industry practices. It is important to consult the latest version of the standard for the most up-to-date information. In addition to the ANSI/IEEE C37.100-2018 standard, there are other standards and guidelines that provide information on protective relaying. These include the National Electrical Code, the National Electrical Safety Code, and various industry best practices. It is important to be familiar with these standards and guidelines when working with protective relays. Understanding protective relaying principles and practices is essential for ensuring the safety and reliability of electrical systems. By following the guidelines in the ANSI/IEEE C37.100-2018 standard and other relevant standards, engineers and technicians can ensure that their protective systems are properly designed, installed, and maintained. This helps to improve system reliability, protect equipment, and ensure the safety of personnel. Lockout relays are critical for safety in industrial settings. For example, consider a scenario where a motor driving a critical pump in a chemical plant experiences an overcurrent fault. An overcurrent relay detects the fault and trips the circuit breaker, stopping the pump. Without a lockout relay, the circuit breaker might automatically reclose after a short time, potentially causing further damage to the motor or the pump if the fault persists. A lockout relay prevents this automatic reclosure. The lockout relay latches in the trip position, requiring a manual reset by an authorized operator. This ensures that someone investigates the cause of the overcurrent, such as a mechanical failure in the pump, before the motor is restarted. The operator can then take corrective action, such as repairing or replacing the pump to prevent the fault from recurring. Only after the corrective action is taken and the system is deemed safe can the operator manually reset the lockout relay and allow the circuit breaker to be reclosed. This prevents further damage to the equipment and ensures the safety of personnel. In addition to preventing automatic reclosures, lockout relays can also be used to initiate other safety actions. For example, when a lockout relay trips, it can send a signal to shut down of the related equipment or activate an alarm system. This can help to prevent a cascading failure or alert personnel to a potentially hazardous situation. The use of lockout relays is particularly important in industries where the failure of equipment could have serious consequences. These industries include chemical plants, oil refineries, power plants, and manufacturing facilities. In these settings, lockout relays are an essential part of a comprehensive safety system. They help to prevent equipment damage, protect personnel, and ensure the safe operation of the facility. Lockout relays are also used in renewable energy systems, such as wind farms and solar power plants. In these systems, lockout relays are used to protect the generators and other equipment from faults. They also help to ensure the stability of the power grid. Wind farms and solar power plants are often located in remote areas, which can make it difficult to respond quickly to faults. Lockout relays provide a reliable means of preventing automatic reclosures, which can help to protect equipment and prevent system instability. The use of lockout relays is becoming increasingly important as the world transitions to a cleaner energy future. As more renewable energy systems are deployed, it is essential to ensure that these systems are protected by reliable protective devices. Lockout relays play a critical role in ensuring the safety and reliability of renewable energy systems. Understanding the function of these protective devices is essential for anyone working in the power industry. The ANSI/IEEE C37.100-2018 standard provides a comprehensive resource for learning about protective relays and their applications. By studying this standard, engineers and technicians can gain a thorough understanding of protective relaying principles and practices. This knowledge is essential for designing, installing, and maintaining reliable electrical systems. Firstly, lockout relays are crucial in applications where unexpected re-energization could be catastrophic. Secondly, they enforce a deliberate manual reset procedure, ensuring thorough investigation before restarting equipment. Thirdly, they can trigger secondary safety measures like alarms or equipment shutdowns.